Hello, I am Sridhar Chitta, and in this video I shall be discussing current and the conduction process using a unified approach to electrostatics and circuits. The topics I will discuss are charge and electric field, structure of conductors, resistors, current and current strength. This is followed by a description of the action of a battery and a mechanical battery. Following this, I will discuss the production of a uniform electric field in a simple DC circuit, and then we will learn how to visualize current. Electric charges are sources of electric fields. It is an electric field that causes a charged comb by rubbing in one's hair to attract tiny bits of paper. A similar electric field is present in current-carrying conductors. The gravitational field allows us to sit, stand and walk on the second floor of a building because it surrounds the earth and can penetrate through the floors below. Because an electric field penetrates through matter, it enables us to maintain a conversation using a cell phone even if we move out of sight of a cell phone tower. Moving charges constitute a current. A current is the flow of electric charge. Electric charges are electrons, protons, and positive and negative ions. So current in circuits may be a flow of electrons and positive and negative ions. Atomic structure of copper, a conductor. What makes copper conduct electricity? The copper atom consists of 29 protons and 29 electrons. The assembly of the neutrons and protons and the inner orbit electrons is the positive atomic core or the lattice ion. The outermost valence orbit electrons can easily gain kinetic energy under the influence of an applied electric field, and so we call the valence electron a free electron. The inner electrons are hardly affected by the applied field. The electrons see in a conductor. In a metal such as copper, there are millions of atoms, and their outermost electrons, one electron in copper or 2 or 3 electrons in a few other metals, are quite loosely bound to the nucleus. These electrons easily gain energy from heat in the surroundings or applied electric fields and roam freely around the lattice ions, forming the electron sea. In electronics work, all that matters is the outer orbit called the valence orbit. Visualizing a conductor. Visualize a long rectangular box or cylinder. Visualize lattice, that is window grill, rectangular pieces. Visualize fixing these lattice strips inside the box, arranging them in layers. Adding several more until the box is tightly packed. What we are visualizing is a conductor with the positive atomic cores, lattice ions, located at the intersection points of the lattice. These are composed of neutrons and protons and include the inner electrons. Now pour some sand in. And that is the conductor. composed of neutrons and positive protons, including the inner electrons called the lattice ions, and the sand is the electron sea of the outermost electrons. Electrons will move when there is a force acting on them, as in the presence of an electric field, and they will continue to move unless acted upon by opposing forces, for example, due to collisions with the vibrating lattice of atomic cores in metals, or opposing electric fields produced by accumulated charges on capacitor plates, or opposing magnetically induced electric fields, or opposing fields in conductors moving in steady magnetic fields. The German physicist Georg Simon Ohm considered that there was a gradient of volume charge inside a current carrying conductor which created a driving field, whereas on the basis of what was known about electrostatics, there could not be a volume charge inside a conductor carrying a steady state current. Kirchhoff and Wilhelm Edward Weber put the driving charge gradient on the surface of the steady state current carrying conductors and showed that electrostatic and circuit phenomena belong to one science, not two, thus unifying electrostatics and circuits. Unfortunately, this unification was later lost sight of as the role of potential came to dominate the analysis of circuits and the surface charges disappeared from view. Resistors. Most resistors are made from conductive materials that have a high density of lattice imperfections and which also have a smaller concentration of free electrons. Current strength in a conductor with low resistance. We apply a driving electric field. A large number of electrons will move past a cross-section per time in a low resistance conductor. The free electrons have a start-stop motion as they collide with the lattice ions, which will be vibrating themselves. Current strength in a conductor with high resistance. We again apply a driving field. A small number of electrons will move past a cross-section per time in a high-resistance conductor. In a conductor with high resistance, only a small number of free electrons would have moved past a cross-section per time given the same strength of the driving field. Such conductors are called resistors. Action of a battery and the production of a net electric field. A battery operates by separating positive from negative charge and then depositing them on its plates. There is an internal and external electric field. A mechanical battery simulating a chemical battery. A hypothetical mechanical battery is useful to explain the action of chemical batteries. The conveyor belt applies a non-coulomb force Fnc to extract an electron from the positive plate of a large parallel plate capacitor and pushes it onto the negative plate. In an open circuit or with small currents, charge builds up on the plates until the Coulomb force EEC is equal to the non-Coulomb force Fnc, where EC is the Coulomb field due to charges on the plates. The separation S is small compared to the size of the plates. Traditional circuit analysis solely in terms of potential cannot provide satisfactory answers to some questions. For example, Härtel reports student asking, what is the difference in the conditions at the two ends of a resistor? It is quite unsatisfying to say merely that the potential is different. Another student question reported by Härtel is, how does the current know how to split when there are parallel branches? Is electric current due to charges in and around the battery? Bring the bulb closer to the battery. Does the bulb glow brighter? The bulb glows with the same brightness even when brought closer to the battery. Now rotate the bulb by 90 degrees. Since the electric field is now perpendicular to the filament, the bulb should stop glowing. The bulb does not stop glowing. Therefore, the electric field from the charges on the battery has no effect on the bulb filament, and some other charges are responsible for producing the electric field which is pushing the electrons in the filament. Constant electric current and the distribution of surface charges. When the circuit comprising a battery, wires, and resistor is made, surface charges appear on the wires and on the resistor. Positive surface charges appear on the wires connected to the battery's positive terminal, and negative surface charges on the wire connected to the battery's negative terminal. The surface charge density gradient at the two ends of the two wires is small, which produces a weak electric field in the wires. The surface charge density gradient across the resistor is steep and therefore produces a powerful electric field in the resistor. This ensures a constant current in the circuit. It is the surface charges that cause the electrons inside, not shown, the wire and resistor to move. Visualization of current and how steady state is maintained. When the circuit comprising a battery and a wire is made, an electric field will be set up at every point within the wire by a surface charge distribution with a gradient. If the battery voltage is 10 volts and the uniform wire is 5 meters, the strength of this field at every point will be 2 volts per meter. This field will act on the electrons and will give them a resultant motion in the direction of -E. The field is not uniform in the space surrounding the circuit, as there are no mobile charges there that can produce a resultant uniform field. Steady state means that some charges are moving, but their velocities at any location aren't changing, and there isn't any change in the deposits of excess charge anywhere. Current in the wires is a start-stop motion of millions and millions of conduction band electrons everywhere within, with a drift superimposed. The drifting of electrons in a current. We want to calculate how long it takes for an electron to get from a car battery to the starter motor after the ignition switch is turned. Assume that the current flowing is 115 amperes and that the electrons travel through copper wire with cross-sectional area 31.2 square millimeters and a length of 85.5 centimeters. The slowest snail in the world is recorded to move 12 meters in 1 hour. In 1 hour, the electron would have moved in the 115 amp circuit barely a meter. the Drude model and the drift speed of electrons. The drift speed is so small, a mere 1 meter per hour, and nowhere near the speed of light. Paul Carl Ludwig Drude formulated a simple classical model of electron motion called the Drude model. According to this model, a mobile electron in the metal, under the influence of the electric field inside the metal, does accelerate and gain energy, but then it loses that energy by colliding with the lattice of atomic cores, which is vibrating because of its own thermal energy. Visualizing current. There will be a net transport of electrons past one cross-section, and there are some other electrons not the same that will be crossing a boundary at another cross-section a few micrometers away, and different electrons crossing at any boundary all around the circuit at the same instant with the same number flow rate. That is sufficient to be registered as a current by an ammeter, or the same current in several ammeters placed anywhere around the circuit. How does the bulb on a distant pole turn on instantly when the switch is thrown? The surface charges set up a change in the electric field in the wires at less than the speed of light, but not less than about half the speed of light. The millions of electrons everywhere within are jolted and begin to drift slowly, seemingly in an instant, and our eyes do not notice the fractional delay.